So this is VADSTI 4 series. We had a spring series in the spring that was in February and March. So for this 4 series, the first 3 weeks, so today will be, or this week will be the last week of the first 3 weeks, is what we call the pre-training sections. So the first week we covered foundations of data science. The last week we covered introduction to Python. And then this week will be probability, statistical inference, and correlation and regression. So for this 4 series, to get a certificate, you will have to complete a project. So I'll talk about the project in the slide that I will show you. The main sections, that is the main live session, that is session that will not be based on recording, starts next week. So if you missed any of the pre-sections, the recordings are there. You can go to it and then review the recordings. I believe they will post the link in the chat area. You can also check Slack for other information regarding the recordings and then other related information. So today, we'll talk about probability, statistical inference, and correlation. So I'm going to share my screen, and then I'll talk about a few things, and then we'll play the recordings. Okay, so can you all see my screen, what I'm sharing?
Yes, yes.
Okay, good. So today is the last week of the pre-trading sections, probability, statistical inference and regression modules, and the facilitators are myself and William Ampe, who is a data scientist at George Mason University. So before we play the recordings, I have a few slides I want to share with you. So first, this article here by Jeff Leake. He said the keyword in data science is not data, it is science. This was written by Jeff Leake in a blog some years back. Jeff Leake was actually part of this training. He was an instructor in one of our modules back in 2021 when we started this program. So he said that most people hyping data science are focused on the word data. They care about volume and velocity. I think that is what data scientists call what the 3 V's. So it's actual volume, velocity, variety, and even some add another V to it, which is for veracity. So the volume, the velocity, the variety, and the veracity, and whatever other buzzword describe data that is too big for you to analyze in Excel. This hype about the size, the relative or absolute of the data being collected fed into the second category of hype. Hype about tools. They throw around EC2, Hadoop, Pig, and had huge data debates about Python versus R. And somewhere you wrote, but the key word in data science is not data, it is the science. Data science is only useful when the data are used to answer a question. That is the science part of the equation. Very interesting, it's very short. If you Google the key word in data science is not data, you will find the complete article. So I'll encourage you to take a look and then to read it. Okay, so I mentioned the project. So at the end of this training, for those who would want a certificate of completion, we require you to complete a project. The project will be part of a series of homework or assignments that the different modules will be provided. So I will provide with 1 or 2 data sets, but if you have your own data sets you want to use for the project, that will be fine too. So you have to complete the project and then submit it to a GitHub that will be available to you before you can receive a certificate for completion of this training. So here, this is what we call for, it's called for the data science workflow. There are several versions of the data science workflow. We have the well-known ones are what the CRIPS DM. The CRIPS DM is used mainly by those in business. And I believe also in economics, we have the Harvard workflow, we have the Jos's workflow, and then there are other ones. But the bottom line, they are all about the same. Some of them, for example, the CRIPD and Harvard, they will start with what? The research question or the research objective. But at the end of it, there have to be what? There have to be some data to be assessed, cleaning the data, modeling it, production components, and then the monitoring. So Joshi actually includes monitoring as a part of the workflow. Some of the others, they don't do that. So again, if you Google data science workflow, you may see this, and then you may also see the different varieties. But again, all of them will start with what? Either the raw data, because you need the data, you have to use the data to answer a research question or address a research objective. So this is what I added to the workflow that I just shared with you. As a matter of fact, this was done in collaboration with the AIM-Ahead infrastructure core. So what do you do? So some databases you actually will need to request, write a proposal to get access to those databases. Some of them are free online, is readily available. The NIH, other federal government agencies have so many of these databases, and they are looking for people like you to tap into it and then analyze the data. These are some of them. So we have, of course, many times one may want to use electronic health records. Along the line, I'll bring someone to give us a presentation of the use and elements of electronic health record. So there is for the AWS, there is BYOD. BIOD means bring your own data. There are tools, resources that are available for you to process the data. If you don't belong to AIM-Ahead, it's free. You can join the AIM-Ahead Connect, and then you can have access and then some of the resources that are provided. So if you don't already have the data, it's already collected, then what? You have to make a request to access those. Of course, it will have to be approved for some places, or they may come back to you and ask you to revise certain things if it is government data sources. In general, in most cases, they will approve it. And then once you get approval, then you have to start implementing and then doing the actual data science. That is where the workflow comes into play. So I say that the workflow we'll have to start with what? A research question or a research objective. So once the data is collected, then of course, data science, you cannot do data science without what? Ethics. So what we call what? Ethical data science. So again, I'll bring someone to give a 1 hour or so presentation on ethical data science. So ethical data science starts from the data collection phase. And you have to use it because there's ethics for data collection, ethics of what? Data analysis, and even ethics of what? Data reporting. So ethics is very essential. It's a key element or a key part of data science. So data science is not just knowing your Python or R or whatever, programming, a language, and then assessing and then running it. Ethics is very essential part of it. Then data processing or data cleaning, sometimes data science, they call it data munching or data wrangling. That is just, once you have the data, you have to look at it, you have to clean the data. Then the next step will be what? Modeling. But modeling wouldn't be the very next step. There is a step that we call what? Exploratory analysis or reporting. So the exploratory analysis and reporting, there is also, I think, next week when we start the live section, the very first section or module is what? Data, I believe is data preparation, exploration, and visualization. So we'll have that next week. Many times, some people will just end here. When they got the data, they process it, they just do what? Exploratory analysis, which is basically descriptive statistics, and then maybe presenting your result by way of what? Graph and chart for visualization, and that alone can end your project. So if that is all that one needs to do, then you can do what? You can prepare your report and then submit it or present it wherever. So for you, especially those of you who would want to use their own data set, if that is where you want to end, you have to give us a reason why you want to end that at that point, and then you can submit it to GitHub. But again, I encourage you to try to also do the actual modeling, because the exploratory data analysis will suggest things that you do. Sometimes one may need to transform variables, recode them, or do other things. Or even the exploratory analysis sometimes may even tell you that, this research question or that I need to answer, or the research objective that I need to address, perhaps maybe the data that I have at hand may not be a relevant data. So exploratory data analysis is very key, very important aspect of data science. Then we talk also about the actual modeling. So the modeling, there are so many different parts. Again, that is another aspect where the statistics are coming. So we'll talk about what classification methods, we'll talk about clustering methods, we'll talk about machine learning, we'll talk about predictive modules. But again, as I said at the beginning, ethics will always be part of the modeling aspect. Why is ethics important? It's very important because sometimes researchers, there is some kind of inherent bias, because once one proposes a hypothesis, they wish that the data that they have will provide the evidence for them to accept that hypothesis or to reject the null hypothesis. So again, from next week going, one of the modules will cover one of these approaches over here. So once all this is done, then the deployment phase, that is where you are actually communicating your results. Someone, there is a code somewhere that says that your research is not complete until it is published. So if you do the research, data science, whatever, and then you are sitting on the results, that is not going to benefit anyone. So you will have to do what? Deploy it or disseminate the result by way of either communication, presentation at a conference, at a meeting, or actually submitting it to an article. So for us or for you, we'll submit it or we'll deploy it by submitting it into a portfolio that you create in GitHub to submit your results. So again, I just brought this up to let you know that so the actual project, the details of it will start from next week. So by next week, before we start, I think I'll put instructions on the expectations for the project.
John, just not
Yes.
not to cut you out, but I think
Sure,
Ben's
go ahead. Yeah.
Ben's hand has been up. So there's Ben Carity. His hand is up. Yeah.
Thank you.
Yeah,
very
sure.
much.
Go ahead.
Thank you very much, Mr. William. So I had a question for you, Dr. John. So there are several of us on the call who are already part of the Aim Ahead program. So my question to you is, and also Mr. William is, do we need to create a separate data science project for this workshop since we're already creating one for our Aim Ahead program?
Yeah, that is what I said, that if you have your own projects, your own data source, data set or database to you, that is fine. Go ahead. So for you, those from Aim Ahead, all that you do or your being here is to learn some of the techniques or approaches to maybe generate descriptive summaries, do data visualization. So yeah, you don't need to get another project, but you have to submit it to GitHub. Now ask the Aim Ahead people if you are allowed to do so. If you are not allowed to do so, then you can send us a note that, yeah, I've completed the project. Maybe you can send it to me or to Dr. Gloria Washington, and then Gloria will tell me or let me know that, okay, yeah, you've completed the project, but maybe for this reason or that, you are not submitting it to the VADSTI GitHub.
Okay, thank you very much. I think Ms. Jovita has her hand up now.
Sure,
Hello.
go ahead.
Hi. So my question, and thank you, Ben, for asking the question, because I was thinking, why create two different projects when we could potentially, start working towards ours? But I have a question, like, is there tutors that could help us maybe with the coding? I'm not new to data science, right? But with Python, I am, right? So I was wondering if there's any tutors that could help us put our code together.
Yeah, we don't call them tutors per se, we call them teaching assistants. So that there will be teaching assistant where William is one of them, Dr. Nwafo, I think he's on the call, so he's also one of the teaching assistants. He will, in fact, he will also even present one of the modules. So all you have to do is go to Slack and then see when the next office hours or teaching assistance sessions are available.
Yes, John. Yeah. So and that brings out this. I think it will be announced at the end of the day. Normally we have it on after class and also on Saturdays. So we'll let John keep going on. I'll link up with my other colleague, and then we'll see whether there's going to be a session today but definitely there's going to be one on Saturday. And Saturday will be like 5 to 7, or we'll post it on Slack. Okay, and also post your availability on Slack as well. Okay, thanks.
Thank you.
Sure. Any other question? Yeah, so again, if you want to ask a question, you can maybe post that in the chat area, or you can raise your hand as you did. And then if it is posted in the chat area, one of the instructors will respond to your question. Okay, so you see my screen, right? I'm still sharing, I suppose. Okay, so this is what I started. I said the keyword in data science is not data. It is science. That was by Jeff Leake, who is at Hopkins. So I sent Jeff a note. I said, well, this is what you are saying. The keyword in data science is not data. It is science. But I think the bridge between the data and the science is statistics. I haven't published this, but I've been saying this for several times now. So if you hear it somewhere, they know that it's from me. Now, again, if you are here on the first week where we played the recordings on foundations of data science, it was made clear that statistics is what? It's a very big chunk of data science. So that is why we are doing this here. Again, this recordings here from the spring series was over 2 weeks or over 4 days, because the first week was for up to 3 hours for Thursday and Friday, and then the second week similarly over 2 days. So we actually have 4 days of recordings. Again, if you check Slack, and I believe that will also be posted in the chat area, you get the full recordings. But for these sessions, because we have only 1 week, we can do only 2 days out of the 4 weeks. So today, I'll just go over about 5 or 6 of the slides, and then I'll start playing the recordings. So this originally was presented on March 24th, 2022 by Paul Com, and then William, who is on the call. Now, why am I playing this? First, just to give you a gist of it, but also if you start playing the recordings, you will notice that the very few slides were cut off. I think probably maybe we forgot to start the recordings early to capture that aspect. So that is the part that I want to fill you in. But the slides are there. If you are someone who wants to read rather than to listen, you can find the slides in there. So it's the slides that I'm using here. Now, if you want to listen to the recordings, then you will notice that the very first few slides are missing. So in the recordings, this is what it talks about: statistics and estimation, inferential statistics, random sampling, variability, theoretical sampling, distribution, hypothesis testing, and p-values, parametric statistics, non-parametric statistics. I think non-parametric statistics was actually on the second day. So you will not play the recordings today, but again, as I said, the recordings are there. Feel free and then review it at your leisure times. Okay, so to give you some flavor, this is what we have here, just only to highlight some of the key statistical elements or terms. So the impact of metabolic syndrome and diabetes on prognosis and outcomes with early percutaneous coronary intervention in the COURAGE trial. So this was published 2011. Now, if you look at the statistical section of it, you see this was a post hoc analysis. So anytime you see the word post, it means after the fact, right? So this was after the trial, which will mean here that will more of a secondary data analysis because the primary aims have already been addressed. Patient characteristics across groups were assessed by analysis of variance. So analysis of variance is a common statistical approach for continuous variables. So see, it says for continuous variable because analysis of variance is for continuous variables and the chi-square test for discrete variables. The Cochrane-Armitage test was used for trend because the Cochrane-Armitage test is what? It's a trend test. Estimate of the cumulative event rate was calculated by the Kaplan-Meier method. So Kaplan-Meier, again, those of you who are familiar with survival analysis or time to event data, that is where you use the Kaplan-Meier. Time to endpoint analysis was done using Cox regression or stepwise Cox regression. Cox regression was used for the adjusted analysis. So here, those terms or phrases highlighted or rather underlined are all statistical terms or statistical procedures. So those are some of the things that the training address or were instructed on. Another example here, again, these are all real analysis or rare data that were used. So for this, the risks of cardiovascular events in primary care patients following an episode of severe hypertension. So here, if you look at the statistical section of that paper, it says the chi-square statistics was used to compare proportions. The Kruskal-Wallis test was conducted to compare means and medians. Now, the first statistical approach for the Corey trial, it talks about what? It talks about the analysis of variance for continuous variables. Kruskal-Wallis test does similar thing just like for the analysis of variance, but analysis of variance is what? It's a parametric approach. Kruskal-Wallis test is what? It's a non-parametric approach. So looking at the data, some of the things that you can do with what your data exploration. The data exploration will show or it will make it clear that the data you have is what is continuous. It may be continuous, but maybe is skewed. So many other things. So parametric approaches are based on specific distributional assumptions. So if those assumptions are not met, then we have to use for the equivalent non-parametric approach. So here, the Kruskal-Wallis test is just a non-parametric equivalent of analysis of variance. So again, we will not cover non-parametric or we will not review the non-parametric procedures tomorrow, but the recordings are there. Look at it. If you have any questions, you can send me a note or to any of the instructors. And the Bonferroni correction procedure was used for all pairwise comparisons. Poisson and negative binomial regression models were used to adjust for observed incidence rate for age. I mean, some of you may be familiar with linear regression or even logistic regression. But linear regression is for what? Is for continuous dependent variable. Logistic is for binary if you are doing a binary regression. But what about counts? If you have counts data, then you can use Poisson regression and other regression methods. So again, all these if even we don't review them in these training sessions, the recordings are there for you. The cumulative incidence of first and multiple cardiovascular events for each category or blood pressure category was obtained by Kaplan-Meier method, already talked about it. And then time to event was measured in years from the date of index until the date of the cardiovascular event or censoring. So hazard ratios were estimated from the cost proportional hazards modules. So these are some statistical approaches. Even here it talks about what the Princeton, Williams, Peterson multiplicative hazards model. Of course, we are not, or we cannot cover everything in this series, but if we are lucky and then this funding to support this program continues, then some of these advanced approaches will cover them. So these two examples are just to give you a flavor of some of the things you may come across in terms of statistical approaches and procedures. So what is statistics? Statistics is just for a summary of individual measurements. For example, we can use the mean as a summary. So what do we mean by individual measurement? Individual measurement is what? Is the measurement on you as an individual. But statistics, generally, we are not doing case studies where we focus on just one individual that is part of statistics also, but in general, we are looking at what? A whole group of individuals. So variability needs to be considered because the summary of the measurement, such as the mean, those are just one number. So if you're using one number to represent thousands of individuals measurement, then you would expect that there will be what? Some kind of variability in the data, because if there is no variability, then there wouldn't be statistics. I tell my student that statistics is what? Is the study of variability. If everything is fixed, then there wouldn't be any statistics to be done because we know what it is anyway. We know that everything here, all of them should be a certain height, a certain weight is fixed, there wouldn't be statistics. So variability would also need to be taken into consideration. Of course, in general, theoretically, you expect the values or the variables to be what? Random. So if you collect what? A random sample of blood pressure, heart rate, gender, race, quality of life, scores, in general, that will need to be random. But again, some things as we do, or if you are looking at textbook presentation, many of them are theoretical. But if you are into research where things are practical, you will know that, okay, the ideal way is to sample, use random sampling, but practically that is not done. So you may end up using a random sampling. Then of course, you also have to summarize for the random variable. So in short, that is what statistics entails. Then we also have to do what? Estimate statistics. That is where inference comes in. The first part, summaries of individual measurement, that is what we call descriptive statistics. Estimating statistics, then the issue of inference may also come in. So what does this imply? So this implies because in general, we want to estimate a certain characteristics of a population, or we want to know the characteristics of a certain population. But because the population is so large that we cannot use the entire population, what we do, we just draw a sample. Again, if you are drawing the sample randomly, that is the ideal case. So we use the measure of the statistic of the sample as an estimation for the entire population. So that is what the estimation here means. So doing that will always present some form of uncertainty. So you can think of statistics as what? Measurement or quantification of uncertainty. Okay, so let's assume this is a random sample of diastolic blood pressure values of 144 patients. So you have this. So how do we summarize this? So one way to summarize this is what? Is to find the mean or the arithmetic mean, the average. So how do you find the mean? So the mean is what? You have to sum all the values here, all the diastolic blood pressure values. You're going to sum add all of them up and then divide by what? The number. So here the number is 144. That will give us a mean of what? 76.3. So that is one way to find what the summary statistics. In fact, the mean is the common measure or one of the commonest measures used to summarize a continuous variable. But the mean alone will not be complete, because I told you that, if statistics, everything was fixed, then there wouldn't be statistics. Statisticians would not have any job. So in reporting the mean, you want to also find a way to indicate, okay, so how much the data oscillates around the mean? How does it go below the mean, above the mean? And that is what? A measure of variability. And one way to do that is to use what? The standard deviation as a measure of variability about the mean. And this is the formula for a standard deviation here. So you take the mean minus the individual value. So each individual value, how much does it deviate from the mean? So it can deviate, it can either be lower than the mean or higher than the mean. That is why sometimes we say that, okay, your score is what? Above average, which means your individual score or one's individual score is greater than the average. So we find the variance, and then we take the square root of the variance. The square root of the variance is what we call the standard deviation. So why do we use the square root of the variance? Because the variance is also a measure of variability. So why do we use the square root rather than the variance itself? So the reason for that is, if, for example, you want what? You are measuring blood pressure. Blood pressure itself is what? The unit is what? Millimeters of mercury. Now, if you are using the variance, then the variance, because it's a square term, then the variance, the unit will be squared. So if the average, for example, is the 76.3 here, then the variance is going to be a huge number, which will not make sense. And one way that we take the square root of the variance and then use the standard deviation is, if the unit of the variance is squared, and then you take the square root, the unit of the standard deviation will be what? It will be the unit of diastolic blood pressure. It will not be squared. So that is one reason why we use the standard deviation rather than the variance. So there is something we call degrees of freedom. Degrees of freedom is just the components of statistics that are free to vary. What that means is, in the example here, if there is 1 degree of freedom, what it means is, if I need, say, 3 elements to find something, if there is 1 degree of freedom, what that means, I wouldn't need all 3 elements, or I may not need. If I have 2 of them, I should be fine. For example, if the sum of x1 plus x2 plus x3 is 100, if I tell you that, okay, so the sum is 100, one of the numbers is 50, can you tell me the other 2 numbers? You cannot tell me the other 2 numbers. Perhaps you can tell me the sum of the other 2 numbers, but the actual numbers will not be able to identify those. However, if I tell you, okay, so the sum of the numbers is 100, or I want the sum to be 100, 2 of the numbers are what, 40 and 50. What should be the 3rd number? I'm sure you'll be able to tell me that. So that tells me that, okay, once I get 2 of them, I don't need the 3rd one. I'm able to find the 3rd one. So that will give us what, a 1 degree of freedom. So I'm going to jump to the recording. So this is the part of the recordings that was mixed. But again, if you go through the slides as I'm doing, everything is there. If you want to listen to the recording, this first few slides were made. So I'm going to jump to the recordings unless anyone has any questions for me. Okay, so if you don't, then I'm jumping to the recordings. Okay, so would this be an add or? So why am I getting? Oh, okay, give me a minute. I think it's giving me.
So in the meantime, if you have any questions, please just post them in the chat and we'll address them.
Hi, Mr. William, I did have a question. So my question is back to aim ahead. So again, several of us on the call are on aim ahead, and we also are afforded many training resources. So I sort of feel like we're kind of going over the same things in this workshop compared to what will be made available in aim ahead. So, I mean, is it okay for us to maybe primarily use the aim ahead resources in lieu of this workshop, or does it really matter to you? Please let us know.
Yeah, so then I would say whatever gets you to the end goal, right? So there are a whole lot of resources all over the place. You pick the one that's appropriate. So if you have, I don't think it's going to be a duplicate. There may be what you have. There are some resources in this session that would enhance the resources that you have. Now, what will hit you is that if you have time, right? If you don't have time, then you have to pick your fight. So if you're doing a research for this class, then I'll try and use as much as possible most of the resources that are made available to this class, so that you can relate to you can relate to it much easier. But if you feel comfortable with the MIHEAD resources, that's fine. The main thing is make sure that whatever you present is relevant to this session.
Great, thank you.
Okay.
Yeah, I will also add that again, this class, this is organized in modules. So the modules is done in such a way that one may not necessarily have to depend on the other modules. So if, for example, okay, statistical concept, you are fine with statistical concept, you know everything that will be presented. You want to skip that is up to you, but the thing is, or the beauty is sometimes if you listen to this, you may get what a different perspective of the subject or of the content. That is why sometimes even things that we know already or we've learned in the past, someone come to present it, we go and then do what we listen to those. But otherwise, if you are fine with the module, for example, next week is going to be what exploratory data analysis and visualization. If you are fine with it, you feel that you don't need those, you want to skip that, and then attend the lecture on classification modules or predictive modules for machine learning, then you can do so.
Sorry, I have a question.
Sure.
My question is, so after all of these modules, like going through them, the first, last week I just watched the recordings for both of them, but I know you said we don't have to always be here, but will we still end up with their certificate at the end of the semester? Or
Well,
the end of this?
The requirement for the certificate is completing the project and submitting it into in GitHub that you completed it. Now, if you are part of the MIHEAD fellowship, and then you will need to submit it in a different place, then let whoever your supervisor or whoever is in charge of that send us a note that, yeah, John Doe has completed their project, is submitted, and then that should be fine also.
Okay, all right, thank you.
All right, any questions before I start the recordings? Okay, can you hear? So the recordings is on now.
Okay. I think the volume, we may be struggling with the volume.
Make sure you choose the option to share your computer audio as well as the screen.
Yeah. I think Zoom has a little privacy thing that when you share, you have to, there will be a button at the bottom that says shared audio. So let's stop the share and then do another share, and there's going to be, yeah. So once you share, just at the bottom there before your status bar,
So you want to stop the recordings?
Yes, and reshare again, because I think once you sharing, if you don't check share audio, the audio won't come through. So
okay, let me pause this first.
Okay. And then when it's playing, do you hear the voice on your at your end?
What values can they take on? So let's say that X1 is equal to 50. So knowing that they sum to 100, then what values can X2 and X3 take on? Well, X2 can take on any value. It could be a positive value, could be a negative value, it could be a decimal value, because we have 3 different components here, and so 2 of them are free to vary. But if we know then that the second number, x2, is equal to 40, then x3 cannot vary, cannot randomly vary. It has to be, in this case, 10, because they add up to 100. So that's the basic idea of what we mean by degrees of freedom. And so in inferential statistical analysis, what we're going to do is compare two or more statistics, or look at the relationship, the association or correlation of random variables. Or we're going to do a prediction kind of study where we have a prediction model where we want to predict some particular outcome given a set of predictor variables, or what we call covariates. And so basically the model here is that our dependent is a function of, or is modeled as, a function of the independent variable or variables plus an error component. And so the dependent variable can be something like maybe blood pressure would be our dependent variable, and we want to look at what things might predict or be associated with blood pressure. Maybe our dependent variable is survival, death or alive. And so we have a dichotomous variable there, and we want to look at a set of independent variables that might predict or might be associated with our dependent variable. When we decide which statistic to do, or what's the appropriate statistic, we also need to consider how our variables are measured, particularly our outcome variable or our dependent variable. And so the commonly, or the common measurement scales that you see defined are, first of all, a continuous measurement where you have an infinite numerical scale and the distances between scale divisions are equal. So for example, if we look at height, or say, for example, we look at height in inches. So what we mean by scale equality here is that say the difference between 59 inches and 60 inches is the same as the difference between 71 and 72 inches. In other words, it's 1 inch. An ordinal scale is where we number our outcomes. They're numerical, they have a certain particular order, but the distances between them are not necessarily equal. And so some examples of ordinal numbers are like cancer stages or cancer grades, or maybe you have 4 cancer stages that are labeled 1, 2, 3, and 4, with 4 being the most severe or the worst. But the distance between the 4 different stages is not necessarily the same. And then we have just simple counts where we just count things, count occurrences. So an example here might be the number of infections in the ICU, or overall in the hospital, the number of infections. And that's usually associated with some time, like over a 3-month period or a 1-year period. Then we have nominal variables, where these are what we refer to as categorical. In other words, you might assign numerical values to them, but they don't have a numerical meaning. And so examples like this are gender or race, where our values are just labels. And then finally, we have what's called time to event data, where we actually have 2 different outcomes or 2 different variables. One, we have the time variable, which is continuous. And then we have the event, which is a dichotomous variable. The event either occurs or it doesn't occur. And so when we look at statistics that we're either estimating or whether we're doing inferential statistics or we're looking at the relationships or associations, we need to consider what type of data that we have. Then also another aspect of consideration here is what is our research design? In other words, what is the question that we're asking? And how do we set up our research study to answer that question? And so the three primary categories here are retrospective studies, which are referred to as case control studies. In retrospective studies, you're taking a sample of, say, patients that have already been in the hospital and have been given some treatment, or they've looked at some particular outcome. Then the second one is a prospective or a cohort study that's where it's non-randomized. So this might, an example would be, say we're going to look at patients that say have a certain type of cancer. They're all at stage 1, and then we're going to follow them for a certain amount of time and look at the progression of cancer over time and look at the variables that might be associated with progression. So that's what referred to as a prospective study, but in this case, we're not. They're not randomized to a, say, like a treatment or control. And then finally, and the strongest design as far as getting at, say, cause and effect, is the experimental design, where we actually randomize subjects or patients to, say, treatment groups. And so in our cancer study, maybe we have 2 different treatments, and we randomize patients to one treatment or the other. And so in this case, we would have a comparison of the 2 groups where we have randomized patients. And so in doing that, what we do when we randomize is that we essentially wash out any pre-existing differences that might have existed between the experimental groups. And so the experimental design, or oftentimes called a randomized clinical trial, is really the strongest one of getting at cause and effect or relationships. So when we design a study, what we are doing really is we want to answer our question, our research question about a population of subjects or a population of patients. But of course, we don't have the resources to sample everybody in a population. Say, for example, our population might be all colon cancer patients. Well, there's no way that we're going to be able to sample everyone in the population. So what we're going to do is we're going to take a sample of that population, and sometimes, or a lot of times, if we have a randomized study, then the sample that we're going to take is going to be drawn at random. Now I put in more or less there because it's not truly random, because then if you're working with human subjects in medical research, for example, they have to consent to the study. And so it's possible that a person might not consent, so they're not in the study. So obviously they're not randomized to one treatment or another, for example. But generally, we can say that if we're doing a randomized clinical trial, then that we have set up our study so that we can, come to a more certain conclusion than with the other types of research studies. But regardless of the type of study that we have, whether it's a randomized trial, a cohort study, or a case control study, the one thing that we can't really control is bias in estimation or the analysis from the sample. And we refer to this as random sampling variability, or more shortly, chance. So in other words, the patients that you select for your study, that you sample for your study from your population, there's always a possibility that random sampling variability is going to negate the results that we get. And so this is where statistics comes in, is basically quantifying the random sampling variability. And so it gives us an index of whether we could say that, well, the chance that random sampling variability has affected our results is very small, or maybe we can't make that statement. And so then we get into the concepts of statistically significant or statistically not significant. So let me give kind of a picture here of what we're doing. So we have our population here over on the left, and we assume that this population has some mean. We'll refer to it as mu. And so when we do our research, we say randomly sample, or maybe we don't randomly select, but we select a certain cohort from this population, and this is our research sample. And so this is the research sample is what we're going to base our conclusions about our study. If we have, say, 2 cancer treatments, which one worked better, or neither one of them worked, or they worked about the same. So the concept here of statistics that we're talking about is the idea that if you were to be able to draw an infinite number of random samples from the population, that the mean of all these samples would approach the population mean. Okay. And so what we're hoping is that the one research sample that we get in our study is representative of the population. In other words, the mean of our research sample is a good estimate of the population mean. And because again, we don't have the resources to do this sort of thing here, where we draw an infinite number of random samples and then compute the population mean that way. We basically get one chance at it. So I have an example here from my diastolic blood pressure that we looked at several slides ago. And so what I've done is I've randomly sampled from the 144, and each time I've drawn a sample of size 5. In other words, 5 different blood pressures from that population of 144. And so what I've done for each random sample that I've drawn here, I've computed the mean of these 5 values that I got in my sample. And then I've ordered them from smallest to largest. And you can see that some of these samples are pretty close to the population mean, which you remember, or if you remember, was about 76. So we have several samples here where the sample mean is really pretty close to the true population mean. But there are some samples that are not. In other words, their mean is really different. It's much smaller or maybe much larger than the population mean. And so this shows us what can happen when we draw a sample, whether it's random or not, from a population, that the mean that we get hopefully is representative of the population, but it might not be. And so it's what we want to determine is how good of an estimate our sample is of the population. And so as you can probably imagine, the larger the sample, the more accurate the estimation of the population parameter. So in talking about variability, we've talked about the standard deviation. And so the standard deviation, as we've seen, is variability of data about its mean. When we talk about a sampling distribution, though, our standard deviation is termed standard error. And when you hear the term standard error, what we're talking about is variability of a statistic. So for example, the standard error of a mean is its standard deviation divided by the square root of its sample size. And so in our inferential statistics that we're going to look at, we're going to focus on the standard error because we're looking at sampling variability, which is dependent on the sample size. And so you can see here that for a mean, the standard error of the mean, as the sample size gets larger, the standard error becomes smaller. And so, as I said, the larger the sample size, the better your estimate. And that's quantified in terms of the larger the sample size, the less variability of the statistic that you get of the standard error. So I have a fairly busy slide here to sort of illustrate this, where I have samples of size 5 from my population of blood pressures. I've calculated the mean, and I've calculated the standard error of the mean. And then from this, I can get what's called a confidence interval. And so I've illustrated this both with the lower bound and the upper bound of my confidence interval. And then I've graphed this over here on the right. So I have values from 59 out to 95 here. And so what this represents for each particular sample is what's called the 95% confidence interval. And what this means is that over repeated sampling, 95% of the time, the confidence interval will include the true population mean. And so I've indicated that here by the X's, which is our population mean is 76. And so you can see that most of the confidence intervals that we have include the population mean, but there's a couple here that don't. And so the idea here is that our confidence interval is going to be, as I mentioned, dependent on the sample size. And so if we increased our sample size to, say, 10, then we'll divide our standard deviation by the square root of 10. So we'll get a smaller standard error than we do here. And so the confidence interval is going to be smaller. But the basic idea here is that the means of samples, if we were able to sample repeatedly, constitute a sampling distribution. And then the standard error of the mean in this case quantifies the variability of the sampling distribution. And we get a 95% constant based on the normal distribution. And I'll picture that in a minute. But basically, it turns out that 95% of the area under a normal distribution lies between -2 and +2 standard deviations. So if we take 2 times our standard error that we've calculated, then we get the upper and lower bounds of our 95% confidence interval. And so as I mentioned before, the mean of the sampling distribution, in other words, the mean of all these means over an infinite number, will approximate the true population mean. And the larger the sample size, the smaller the standard error. And so this is just in words here what I have in the illustration in the previous slide, that the idea is that over repeated sampling or over an infinite number of samples, a 95% confidence interval includes the true population mean 95 times out of every 100 random samples. So that was the, in calculating a standard error of the mean, I was using the normal distribution there, but there are other theoretical sampling distributions that are used in statistical analysis. And by these theoretical distributions, we mean that they are, that they have a mathematical formula. So because of that, then we can easily calculate areas under the curve and come up with probabilities of random variables for any given distribution. And so I'll just spend a little time here on the normal distribution, since that's probably more familiar with to everyone. So in a normal distribution, it's defined by two parameters, its mean and its standard deviation. And it's a symmetrical distribution, which the measures of central tendency, the mean, the median, and the mode are all equal. And so in this picture of a normal distribution, we can see this. So in this particular normal distribution here, I have a mean of 85 and a standard deviation of 5. And in a normal distribution, one standard deviation occurs where the curve becomes or changes from convex to concave or concave to convex, whichever way you're going here. So that's the definition of a normal distribution is really nice, has really nice properties. And it turns out that about 68% of the area under the normal distribution is contained in -1 to +1 standard deviations about the mean. And so when we then look at, as we did before, calculating 95% confidence intervals, it turns out that between -2 and approximately -2 and +2 standard deviations, we have 95% of the area under the normal curve. So that means that if that's the case, then we have 2.5% in each tail of the distribution here, each side of the distribution, 2.5% at -2 or less, and 2.5% at +2 or greater. And so that's where we are coming up with our 95% confidence interval that we're saying that 95 times, or how we're calculating our confidence interval, the upper and lower bounds, is that we're taking the lower and the upper 2.5%. Okay, so then other theoretical distributions that we have that you may or may not have heard of, like a chi-square. Most everyone has probably heard of a chi-square distribution. We use that when we look at contingency tables or look at goodness of fit. Then a t-distribution, which is symmetrical like a normal distribution. It just has thicker tails because it's dependent on sample size. But we use a t-distribution to compare means and correlations. And then the F distribution that we use in looking at analysis of variance. And these distributions, there are other distributions, but these are the most common ones you'll see in statistics. They're sample size dependent, but for each one, as sample size tends towards infinity, the distributions become or tend to become a normally distributed. So that then leads us to talking about statistical significance and p-values. And we're going to look at areas under the curve, these sampling distribution curves to come up with what we term statistical significance. And so in a very general, at a very broad level here, all statistical analyses involve two sources of variance of the outcome variable in the data. And so we have known variance, that's variance between, say, treatment groups or differences in ages, difference in race, or other variables that we may have in our analysis. And then there's unknown variance, which we refer to as error variance. And there's always error variance in any statistical test or any statistical model that we come up with. And basically a statistical test then, whether we are going to test whether something is significant or not significant, is basically our known variance divided by our unknown variance. And then the value that we get, the p-value that we get from this statistics of known variance over unknown variance, which will be one of the distributions, a normal distribution or t-distribution or chi-square distribution. The p-value associated with that t-statistics means the probability of obtaining a value of t or larger just by random sampling variability. So as probably most everyone is familiar with, the most common p-value that is used to define statistical significance in most areas of the literature of research studies is 0.05. And so what that means is that if you get a p-value of 0.05, that means that the probability of getting a t-statistic or a larger one just by random sampling variability is only 5 out of 100 chances. Okay. If the p-value turns out to be, say, for example, 0.01, then that means that there's a chance that our test statistic occurred by random sampling variability just 1 out of 100 times. So we'll kind of get into some examples of this, but I wanted just to really emphasize this of what we're doing when we do statistical tests, or you see p-values associated with statistical tests. So let me give an example here of testing a hypothesis. And so let's say that I have two groups here of blood pressure values for my population. And I have a treatment group and a control group. And my sample of 5 patients in each. And so the mean of the treatment group is 81 and the mean of the control group is 86. And so what I'm interested in here is being able to say, well, did the treatment lower blood pressure? And so if I just look at the numbers as they are, I'd say, well, sure, it did. It's 5 points lower in the treatment group. But the problem is because these are samples, then there's variability associated with these means. And so the question I'm asking is the difference between 86 and 81 just random sampling variability, or can we consider it a real difference? And so in statistics, we have what's called the null hypothesis and the alternative hypothesis. And the null hypothesis is that there's no difference between them, these means. In other words, the 5-point difference here just occurred because of random sampling variability. Whereas my alternative hypothesis is which I hope to be able to show or to prove in a sense, But there is a difference between the means of the treatment and control groups, and that this difference is unlikely to have occurred just by chance. So in making our decision, our statistical decision here, we're going to start out by assuming that the null hypothesis is true. And so our statistical tests are going to give us the probability of attaining the value of the test statistic, or whichever that comes from, a t-distribution or a normal distribution, by chance, and then by inference whether differences are what we call, or what is called, statistically significant. And so when we do hypothesis testing, we can illustrate the decisions that we make in this little table here, where the rows represent the decisions that we make based on our statistical test from our samples, and the columns represent what the true situation in the population is. And so if we start over here in the upper right, where based on our statistical test, we say that there's a difference, but in the population, there's actually no difference. And so we've made what we call a type 1 error, and we call the probability, or the probability of making this type 1 error is called alpha. So, and this is the p-value that you see in the literature when someone says that, p is less than 0.05 or 0.01 or whatever it might be. That's the probability of making a type 1 error. We're not so concerned with where there's no difference, and there's no difference in the population. But the other kind of error, serious error that we can make, is what's called a type 2 error, and the probability we assign to this type 2 error is called the beta error. And so this is a situation where, based on our statistical test, we conclude that there's no difference in the population, but in the true situation, there is a real difference. And so if we make this kind of conclusion, we've made what's called a type 2 error. And it turns out, as we'll see, that the type 1 error here is arbitrary. You can set it at whatever you want. Like I say, 0.05 is the most common one that you'll see, but you could set it at 0.06 or 0.1 or 0.03 or 0.001. The beta error, on the other hand, is also a function of what you set the type 1 error at, but the type 2 error, the beta probability, is also dependent on the sample size. And so we can decrease the probability of a beta error by increasing the sample size. And then this particular correct decision, where a difference exists based on our statistical test, and there is a true difference in the population, then we've made a correct decision, and that probability is 1 minus beta, and this is referred to as the power of our statistical test. And so the beta error here is really important in determining whether you made a correct decision or not. However, the focus is on the type 1 error because you don't really want to make this kind of an error. This is, for the most part, considered the more serious error of making, where you say there's a difference, but in the population, there's no true difference. So in my example here of a treatment and control group, where the means are 81 and 86, and the standard deviations are 5 for the treatment group and 6 for the control group. And so we want to do calculate a t-statistic. We're going to do it just a t-test for means here. And so which t-distribution do we use? Well, it depends on the sample size, and our sample size is 5 for each group. So we have to calculate our degrees of freedom for our statistical test. And as I illustrated before, the concept of degrees of freedom is, what we mean by that is the number of components of a statistic that are free to vary. And so I've given the numerical example here from our data where I have subtracted each value from the mean, in this case, the control group. And you square each difference, and then we divide by, in this case, 5 minus 1 instead of by 5, or we divide by 4. So this is represented here by the first 4 values in our equation here can be free to vary, but once we know what those are, then the 5th one is not free to vary. So that's where we get our degrees of freedom as being, in this case, 5 minus 1 or 4. And so when we do our t-test, then what we're going to look at is our known variability, which is the difference in the two means divided by our unknown variability, which is the standard error of the difference in two means. And so our degrees of freedom is going, our total degrees of freedom for our test here is going to be n minus 1 for each group. So in this case, we get, since there's 5 in each group, we would get 4 plus 4, or we'd have 8 degrees of freedom for our statistical test. And so here is just the computation, what the computation would look like, where we have our known variance here of 5 in the numerator. That's the difference in our means. And then the denominator is our standard error of the mean, or it's estimating our unknown variance. And so we're squaring the standard deviation, taking that times the degrees of freedom, that's divided by our total degrees of freedom, and then we multiply that by the reciprocals of the sum of the reciprocals of the number in each group. And so that gives us our standard error. And so if we divide our minus 5 here by this number here, we get a t-value of minus 1.4. And so if we look at our t-distribution that has degrees of freedom to 8, and the value of our t is minus 1.4, we find out that the probability associated with that, since it's negative, would be this part of the t-distribution curve over here, and it turns out that that's 0.0975, or we have a little less than 10% of the area under the curve, our t-distribution curve, and that gives us our probability, our p-value, of getting a difference this large just by chance. And so then we have a decision to make. Are we going to call this statistically significant or not? Well, again, I say it depends on which you're going to use as your cutoff for the alpha error. And so our calculation here is for what we call a one-sided test, 0.0975. If we do a two-sided test, then it's just 2 times that, and we get 0.1950. And so in this case, we would fail to reject the null hypothesis at the 0.05 level. And why would we do a two-sided test instead of a one-sided test? Well, because if we're doing research, then at least theoretically, we don't know which is better, the treatment or the control. It could be that the control is going to be better than the treatment group. So that's why we do a two-sided test. Basically because we don't know the direction of the difference between the two groups we're looking at. So what conclusions are we going to draw? Well, can we say that there's no difference between the treatment and control? The treatment does not lower heart rate? Well, actually, no, we can't say that. And the reason that we can't say that is because of the small sample size. And so what we can say is that in our research here, we found no evidence for a treatment effect. And so the conclusion that the difference could have occurred just by random sampling variability. And so because we have a small sample size, then we really don't have any basis for saying that there is a treatment effect, or even that there is no treatment effect. We just say that our results are inconclusive in this case. And so in this case, then we our conclusion would be that we have no difference between the two groups, and because we set our alpha level at 0.05, we would fail to reject our null hypothesis. Okay, so let me see, we're coming up on an hour here. So let me go over how we test for categorical outcomes and just do a simple 2-category test here. Whether the test is positive or negative.
William, if we can pause and take a 10 minutes break.
As a 50 mark. Okay, so if we have everyone here, yeah, we have 20. So I'm going to start, and then at the end of it, we'll give you what we would like you to try at home. Okay, so John, I'm going to continue from here.
Sure.
Okay, cool, thanks.
Whether the test is positive or negative, whether we have disease or no disease, survival, dead or alive. And so what my example here is, say, 2 treatments, say A and B, and treatment A had 84 out of 184 patients had a positive outcome, and in treatment B, we had 72 of 202 patients with a positive outcome. And so the research question we're asking is the proportion of positive outcomes different for A and B. So we do this in basically the same way that we did the t-test. So our proportion in A is 84 out of 184, or about 0.45. And our standard error, in this case, the standard error of a proportion is just the proportion times 1 minus the proportion divided by the total sample size. And so our standard error for population A is 0.037. We do the same thing for proportion, or for treatment B. The proportion there is 72 out of 202, or 0.35. We calculate that standard error, and then we subtract the proportion in A minus the proportion in B and divide by the standard error of the difference. And so it would, computational wise, it would look like this, where our standard error is the proportion times 1 minus the proportion times the reciprocals of the sum of the reciprocals of the sample size. And so our difference in proportions is 0.45 minus 0.35. We get 0.1001. The overall proportion is 156. That's 84 plus 72 divided by the total population, 386. So that's the proportion in positive in our entire sample. We take 1 minus that, we get basically 0.6. And then the sum of the reciprocals there is 0.01. So we calculate our normal distribution statistic of 0.1 divided by the standard error, and we come up with a value of 2.0. And so if we look at the normal distribution and the probabilities, or the areas under the normal curve associated with 2, we come up with a p-value of 0.045. And so in this case, if we had set our p-value at 0.05, then we could reject the null hypothesis that the difference in proportions is due to sampling variability, and conclude that treatment A resulted in a statistically significant greater proportion of positive outcomes than treatment B. In this case, 0.45 versus 0.35. So that's a test on how you would do a test that's for categories or for proportions. And so I think this will be the last one I'll go over before our break here. If we have a situation like we had there, where we had a 2x2 matrix of values, we can also compute a chi-square. And so to do this, it's the same kind of exercise in terms of what we're doing. It's just a little different for the chi-square calculation. So we have to calculate our expected values, which are row totals times column totals divided by the total sample size. And what we're going to do is subtract that from the observed frequency in each cell. And it turns out that this statistic that we get is distributed as a chi-square with degrees of freedom equal to the number of rows minus 1 times the number of columns minus 1. And so in my example here, I have the same numbers as I had before. And so my calculation for this chi-square statistic is going to first of all involve the expected. So for cell 1, the expected value is the row marginal times the column marginal, and then that's divided by the overall sample size. And so we do that for each cell, and then we subtract that expected from the observed, square that, and divide by the expected. And if we sum those up over the 4 cells, we get a chi-square here of 4.0. And you can see that we get virtually the same p-value that we did when we did it using the normal distribution. Okay, and just finish up here. If the study is prospective, then we can calculate what's called relative risk from the 2x2 table. And so that's basically looking at the risk factor and its probability of disease versus a risk factor being absent. And so those are the cell counts divided by the row marginals out here. And so in this case, we get a relative risk of 1.3. And so that means that if we have the risk factor present, we have that those that have a risk factor present are 1.3 times more likely to have the disease than not. And if we do a retrospective study, then we calculate an odds ratio. It's a slightly different calculation, and it gives a slightly different result. But we do this because in retrospective, we don't have a true estimate of the proportion diseased and the proportion not diseased in the population. And so I won't go through these in detail here, but you can follow the calculations. And so we get an odds ratio of 1.5, whereas our risk ratio is about 1.3. So it's fairly similar, but not quite the same. Okay, I think, let's see, wherever am I at here? And this is just another comments about the difference between odds ratios and relative risk ratios. Okay, let me stop there. I was going to keep going here, but it's taken just about an hour, over an hour. And so let's take a 10-minute break and we'll start here talking about p-values, what they are not, and what they are. So I have a little after 5 after, so about a quarter.
Yeah, so John, do you want us to move a little forward, or how do you want us to proceed from here? Let's see. I think what we might do, let's keep going. I think John.
Yes, I said, yeah, let's keep going.
Okay. Let's keep going. Okay. So then
I have a little after 5 after, so
Okay, so we'll keep going. Let's see. Gee, okay, give me a second. Let's see that. Yeah, I'm not sure what I did. Okay, let's. Yeah, this is the thing.
the p-value is the part of the study that determines whether you have, I guess, positive or negative findings. And that's interpreted, I think, or I guess I would say maybe it's a bit overinterpreted, because I think a lot of times the p-value is assumed to be the index of whether something is important or not. And that's not the case. So sometimes you'll see that the probability that people understand the p-value as the probability that the alternative hypothesis is true or that the null hypothesis is false. Neither of those are the case. Neither of those are true. Or they look at it as an indication of importance or meaningfulness. And so oftentimes you'll hear the phrase statistical significance versus clinical significance. And so you can get something that is statistically significantly different, but from a clinical standpoint or from a useful use standpoint, it isn't meaningful at all. And another thing that you'll see in the literature quite often is when they get a really small p-value, they'll call it highly significant. Well, that's kind of misleading too, because when you do hypothesis testing, it either is or it isn't. It's dependent on what you set as your alpha error level for your p-value. So if you get a really small p-value, what that means, the way that you can actually interpret that is that there's a very small chance that your results were due to random sampling variability or chance. But it's not zero, so. And then sometimes you'll see if they get like a p-value of 0.06 or something like that, they'll say there's a trend towards significant. Again, it's if you're the way that significance is meant to be used is as a decision to accept or to fail or to reject the null hypothesis or to fail to reject the null hypothesis. And so if you set your p-value, your alpha L error level at say 6%, then 0.06 would be statistically significant. But if you set it at 0.05, then 0.06 is not significant. So as we talked about before, it's the probability, the p-value is the probability of obtaining a test statistic, whether that's a t, a chi-square, a normal distribution, z statistic, that you obtain a test statistic is large or even larger than that which is calculated, and assuming that the null hypothesis is true. And again, the idea here is related to the concept of repeated sampling. If you were able to sample over and over again an infinite number of times, this is what you would get. And it's also dependent on the sample size. And so we'll talk about that, probably next week. But primarily just remember that the p-value is arbitrary. And even though 0.05 is sort of the standard used in a lot of research areas, it can be set at something other than that. Maybe you want to set it at 0.01, but regardless, whatever it's set at, that's an arbitrary decision. Okay, so there was our break. I was pretty close to that. Okay, so I want to then take the last part of my time here talking about different statistical methods. And so we'll break these down into two different broad categories: parametric statistics and non-parametric statistics. And so parametric statistics assume that there's some theoretical distribution for the data or the test statistic, like it's normally distributed or chi-square distributed. Non-parametric, of course, that means that we're making no assumptions about the distribution. So I'll start out looking at correlation. And basically, when we talk about correlation, because this is really fundamental to all statistical tests, that at the simplest level, correlation is assessment of the linear rank ordering of two variables, how the values of one change in relationship to the other. And this is quantified by the correlation coefficient. So if you have a correlation coefficient of 0, that means there's no relationship between the two. If you have get a correlation coefficient of -1, that means you have a perfect inverse relationship. That is, as the values of one are increasing, the values of the other variable are decreasing. And if you have a value of +1, then you have a perfect positive relationship. That is, if the correlation is positive, that means the values of one variable are increasing, as are the values of the other variable. So in terms of looking at a correlation here from a numerical standpoint, I have data here of 25 patients, measurements of cholesterol, their weight in kilograms, and their age in years. And so if we want to, say, look at the correlation between cholesterol level and age, and we calculate that out, we would find it's 0.84, which is a pretty high correlation. So that means there's a pretty strong relationship between cholesterol level and age, and it's positive. So as a person increases in age, their cholesterol level is going up. So in this case, what we're going to do is we're going to look at one variable as having an effect on the other variable, or in other words, we're going to look at one variable as a function of the other. And so in this case, we're going to look at cholesterol as a function of age. And so I've plotted some points here for each individual, their age and their corresponding cholesterol level. So this is one. And so what we're going to do then is we want to, in addition to looking at the correlation, the relationship, we want to look at the linear relationship. So we want to find a straight line that fits the data, that best fits the data. And this is going to give us more information than just the correlation between the two. So this is fairly detailed here, but so that you I want you to basically understand what we're doing when we do regression, really regression of any kind. So Y here represents the mean cholesterol level. Okay, so that would be represented by this horizontal line here. And so the question that we're asking, does age add any information to whatever the cholesterol level might be over and above the mean level? And so there's different quantities that we can calculate here to give us that answer. And so we'll represent an individual point, their age and cholesterol level by Y sub I. So that's one up here is a particular patient. So their age about 60 and they have a fairly high cholesterol level in the 400s or better. And then our straight line here, which we call our regression line, will represent by Y prime. And so this is a theoretical line, you might say, or we'll call it a theoretical curve, even though it's a straight line. And so what we can do is we can find the distance between the individual value for age and cholesterol and look at that distance to the mean, okay, to the mean level, which is about 320. We can then look at the distance between the predicted value, the y prime, and the mean. And then we can look at the difference between the observed value and the predicted value on the regression lot. And so you can see that what we've basically done here is we've partitioned this distance into two separate distances here between y and y prime and the mean. Okay. And so we can then calculate what's called a sum of squares. And so the distance between the observed value and the mean value, this distance is equal to this distance plus this distance, except that we're going to square them. Otherwise, we'll come out with a value of 0. Okay, so that's why they're squared. But that's basically what this is. The distance between the observed value and the mean is partitioned into two different components. The difference between the observed and the regression, or the predicted and the mean. So we call this the total sum of squares. That's this part of the formula. This is called the sum of squares regression. In other words, the difference between the predicted value and the mean value. And then the difference between the observed value and the predicted value is error. In other words, based on our regression here, we predicted that this individual would have, at this particular age, would have a cholesterol level of about 380, but in fact, it's over 400. So this is actually what we call our error, or sometimes referred to as a residual, the difference between our observed and our predicted. And then, as you can see, then the total sum of squares is equal to the regression sum of squares plus the error sum of squares. If we divide the regression sum of squares by the sum of the regression plus the error sum of squares, we get a value called the R squared. And what is this? Well, this is actually the correlation between age and cholesterol squared. And so if we take the square root of R squared, we'll get the absolute value of R. And whether the correlation itself is actually positive or negative would be depending on which way the line slopes here. So here we have a positive slope as age is going up, so is cholesterol. If it was the other way around, cholesterol was going down and age was going up, then the correlation would be negative. So we don't really know the direction here from doing our regression analysis, but the square root of the R squared will give us the absolute value of the correlation. Okay, and so when we plot these, then we get a regression equation, and this line represents our fitted values and then our predicted values. And then basically you can see that some of the observed values are very close to the predicted value, but some are not quite so close. And so then we get an equation, a value of cholesterol in relationship to the age. And so it turns out that the regression equation is 102.6 plus 5.3 times age. Okay, well, what does that mean? Well, the first number here we call the constant, or the intercept. And that's the value of, in this case, cholesterol when age is equal to 0. But of course, zero age is kind of a nonsense value here. So we usually do something else to make it more reasonable. But the 5.3 coefficient here that's multiplied by age. This is referred to as a regression coefficient, or in a simple linear analysis like this, that's the slope of the line. So what that means is that for every year increase in age, cholesterol goes up by 5.3 units, in this case, mg per 100 milliliters. So our regression equation gives us something, or gives us more information than just the correlation coefficient alone. It gives us this intercept point, and which in some cases might be important. In this case, it's not so important, but it gives us the slope. In other words, the change in your dependent variable, in this case, cholesterol, with every unit increase in age. So what that means is that you can multiply any age along here by 5.3 and you would get the predicted value that would follow along this line. Okay. And then, of course, we can compute a confidence interval for our regression line because there's variability there. And so this would be the 95% confidence interval of our regression line. And you can see that what happens here is that in regression, the confidence interval is not, or the upper and lower bounds are not straight lines across the entire range of age here. They're smallest at the mean age, which is around 40, but as you get near the extremes, they become, the confidence interval becomes wider. So if you see a regression, a regression line in the literature that has straight lines here for the confidence, excuse me, the confidence interval, then they've not computed it correctly, because it should have this nonlinear look to it. Okay, so the relationship that we looked at here, the example that we looked at here, cholesterol and age, that's what is comes under the heading of what we call the general linear model, or GLM, that you probably have heard of. And so basically, this is our equation here, where we have a dependent variable that's modeled as a function of some independent or variable or combination of variables. And so we represent this by y being our dependent variable here, and then the b's are regression coefficients. So the b sub 0 here, that's our constant. So in our previous example there, that was what, 102 or something like that. And then the regression coefficient for each covariate or independent variable that we have in our equation. But the point here is that the y is always a continuous outcome. And x's represent the covariates, and the b's or betas are the estimated regression coefficients. And so when you see an equation like this, where you have more than one independent variable, the interpretation is that the beta coefficient here represents the change in y for every unit increase in x. So when you have multiple independent variables, they're adjusted for all the other independent variables in the model. Now, in the general linear model here, the covariates or the independent variables can be a mix of continuous, ordinal, or even categorical variables. And so the statistical test that we would do in this case is we're going to test whether these regression coefficients are 0, or if they're different from 0. Because obviously, if these regression coefficients are 0, then whatever the quantity, it has no impact on y, so this would result in 0 wherever the regression coefficient is 0. And so the regression coefficient then can be positive or negative. And you can have, as I say, a mix of continuous ordinal or categorical variables. So in the general linear model, there's some special cases, one that we've already looked at. So if the X here is dichotomous, it's either, say, a treatment control. You have two groups, then this represents a t-test. Okay. And so if the independent variables, the X's here, are all categorical, then we have what's called analysis of variance. And the X's here can be either dichotomous or they can be categorical. It doesn't matter. If some of the X's are continuous, then we have what's known as analysis of covariance. So then, so what if we have an outcome that's not a continuous variable? And so if we have a dichotomous outcome, success, failure, dead, alive, positive or negative, then we will do what's called logistic regression for our analysis. And now what we're going to model is the probability of one of the dichotomies. So if you have, say, a treatment and control group, then maybe you're going to want to look at the treatment group as being coded 1 and the control group as being coded 0, so that we have a dichotomy there. And so the probability is, in this case, the exponentiated outcome y divided by 1 plus the exponentiated y, where y can be either a very simple or a more complex regression equation, just as we had in the linear case, where we have the same interpretation here. And so when we get this equation where y is a dichotomous outcome here, and we exponentiate the regression coefficients, then we get the odds ratio. So again, we can see that what sort of difference here is that we're predicting a probability, not a continuous outcome. We're predicting the probability of being in one category or the other. And so our statistical test here then is whether our regression coefficients are different from 1. Okay, because if the odds ratio is equal to 1, then that means that the odds of being in one group or the other, or having the outcome, are the same in both groups. And then when we compute a 95% confidence interval for odds ratios, if that interval includes 1, then we say that the odds of the event in either group are statistically the same. So that's slightly different from the general linear model, but when we do what's called the generalized linear model, we're looking at a different kind of outcome, an outcome that's measured in some other way other than continuous. And so just as we looked at before, we can have a special case of logistic regression where if the X is dichotomous, if the independent variable is dichotomous, then we just end up with a 2x2 contingency table that we looked at earlier. And then we can do logistic regression with more than just dichotomous outcomes. We can do what's called order logistic regression, where the outcome is ordinal in nature, multinomial logistic regression, where y is nominal, they're in categories, they're not particularly ordered. You might assign them a number, but the ordering, or there's no order to the categories. And then we can do what's called Poisson regression, where the outcome is a count over some particular time period. And so, for example, we might look at ICU infections over a 3-month period, or some sort of outcome like that, where the outcome is just a count. And in this case, we get, for Poisson regression, we get regression coefficients similar to logistic regression. And if we exponentiate them, we get what's called an incident rate ratio instead of an odds ratio. In other words, a ratio of 2 rates. Okay, and then the time to event models, which are sometimes called survival models in manufacturing. I think they're called failure time models. But we have, in this case, an event, which is dichotomous. And then we have the time to the event. And so that implies that you have to have a point of origin and that the event has to occur at some point in time. And that the event, the terminal event, occurs after the start. In this case, we have some other issues, or another issue to think about, and that's what's referred to as censoring. Because if we are following, say, patients, cancer patients or heart disease patients over time, they might be, some patients might be lost to follow-up or drop out of the study. So the exact survival times are not known, but we can still use the time that the patients were being followed or were in the study to use in calculating our survival function. And so the survival function is a probability that a patient survives from the time of origin to some point beyond that particular time point. In time to event models or survival models, we also calculate what's called the hazard rate. And that's the probability that a patient dies at a time t that's conditional on having survived to time t. In other words, another way of saying that, it's the instantaneous death rate or failure rate for a patient that survived to a particular time. And the two, if you know one, you can calculate the other. And given the way in which they're related there, the hazard function and the survival function. And then we also talk about the median survival time, the time at which the survival rate is 50%. And so I want to use any small example here. So we're going to calculate what's called the Kaplan-Meier survival function. In other words, we're going to calculate the cumulative survival rate over our time period here. And so we start out at time 0 and we're going to 36 months. And we have these patients here that have, oh, this would be their age, yeah. So for our calculations here, that's not relevant. But so at time, oh, this is not their age, this is the number of patients. So we have 74 patients starting out in our study. And so at time 0, there are no deaths, nobody's dropped out. So the proportion surviving is 1, and the cumulative survival is 1 at time 0. Okay, at 7 months, we still have 74 patients, but we have 1 death. And so now the proportion surviving is 73 over 74, or is 0.9, almost 0.99. And then to calculate the cumulative survival, we just multiply the previous cumulative survival by the proportion surviving. So it's this 1 times 0.98. That's why we get the same value over here for the cumulative survival. Then at 11 months, now we don't remember, we only have 73 patients in our study. And now at 11 months, we have another death. So now our proportion surviving is 73 over 74. We get this. And then now our cumulative survival rate is 0.9865 times 0.9863, or we get 0.973. And so on down. Our survival times here at 12 months, 18 months, and so on. And you see at 28 months, we have 4 deaths. We also have 1 censored. Okay, so we, at month 28, we actually lose 5 points. So at month 36, we only have 56 patients survive or left in our study that are have either died or have been lost to follow-up. So what we want to plot then is our survival, our cumulative survival proportions by our survival time. And so we get a graph that looks like this, and they have confidence intervals around it. And the horizontal or vertical dashes here represent patients that have either died or are censored. Okay, and so you can then at any particular time point read what the expected proportion surviving would be. And so you can see here that at 50% survival, everybody's actually surviving. So we don't really have a value where or a time when we reach the 50% level in this case. We can then also do survival where we have more than where we can have multiple covariates or multiple independent variables. And so in terms of the equation, it looks just like the regression equations that we had before, except now that we're going to take our baseline time 0 or a survival time and exponentiate the regression coefficient times times Z, I'm sorry, whether it's 0 or not. And so again, what we're looking at is whether the regression coefficient here is 0 or is different from 0. And so if we have this kind of multivariables model of Cox proportional hazard, then we would get something that looks like this, where in this case, it's just different levels of GSH. And so you can see that the higher the GSH level, the worse the survival rate. And so when you look at a survival function done in this way, you can see that these are all what we call parallel, and that's what the Cox model requires, is that you have proportional hazards, that the hazard rates are proportional regardless of or over time. Okay. So just a little bit about distribution free statistics or non-parametric statistics. So in this case, we make no assumption about the distribution of the outcome variable. And so you're probably familiar with, or you'll see if any statistics books on non-parametric statistics, different non-parametric statistics like the Mann-Whitney, the Wilcoxon matched pairs, Kruskal-Wallis, then for correlations, Spearman and Kendall correlations. And if you have correlated proportions, then McNeamer test. But the one thing about all of these tests is what they're actually testing are not the actual values of our outcome, but they're testing the ranks. And so all of these can be considered rank tests. And so they're non-parametric in the sense that, like for the Mann-Whitney here, if you do just a t-test between for some outcome that say is continuous, but not normally distributed, or is really different from being normally distributed, than what's being compared, say, in the two groups or the ranks. So you rank all of the outcomes from high to low, and then get a ranked score of those that fall in one group and those that fall in another group, and see where they fall, or see if there's a difference in the ranks. The thing is that these are somewhat limited, and so when sample sizes get to be around 30 or so or more, then everybody uses the normal distribution to calculate the p-values for these tests. So in that sense, they're maybe not truly distribution free if you have a fairly large number of subjects in your study. So what's truly non-parametric is when we do what's called the bootstrap and the jackknife. And so the bootstrap is basically randomly selecting an observation from our sample data, and then we put that or a group back into the pool of data, and then we do again, we randomly select an observation and then put it back in the pool that can be selected. So you see that the bootstrap may select the same patient any number of times, although it might be just a few times, but you have that possibility. But if you do the bootstrapping over a lot of times or many times, then you get an expected distribution of your outcome variable. The jackknife is sort of the opposite of that. I'll have an illustration of that. Basically, what we do with that is we have our distribution of outcomes of data, and then we take one out and recalculate our statistics. Then we put that one back in and take a different one out, and so on until we get through all of our subjects in our data, and then use a summary statistic of all those that we've calculated from leaving each one out. So this is the idea of bootstrap. So you can see that we call sampling with replacement. So you have your sample over here, again, not your population, but your sample. And so you randomly sample that many times with replacement. And you sample, each sample is the same size as your original sample. So if this is, say, 100 patients in your sample, then each bootstrap replicate has 100 patients in it, although some of them might be the same patient. And so in doing this, we can then calculate statistics, we can calculate confidence intervals, we can test hypotheses doing this. And so in this sense, it doesn't matter what the distribution of our sample is, of our outcome variable we're interested in here. We're just creating a distribution of that statistic. But this requires, depending on what you're doing, a fairly large number of replicates. So usually it's anywhere from 100 to 40,000 if you're doing hypothesis testing. But of course, on the computer, you can do that sort of thing fairly easily. And there's routines built into most software to do bootstrapping. I'm pretty sure there'd be one in Python. So leave out one. This illustrates what we mean here. So if we have 10 observations, here's our statistic with all of them in there. Then we take out the first patient or the first subject here, and we recalculate our mean, and we take out the second, recalculate the mean, then take out the third, fourth, and so on. And so we have these 10 different estimates of our mean. And so that from the distribution of all these leave out one means, we can get a 95% confidence interval, whether the distribution is symmetrical or not. And so that's leave out one, which again is fairly easy to program. Okay, then I want to finish up by talking about considerations for doing statistical analysis. So the first thing is what we call the effect size. In other words, if you're, say, testing a treatment and control group, what sort of difference is meaningful from a clinical or whatever the context of your research is? What's a meaningful difference, or what's a meaningful, odds ratio or a meaningful risk ratio? And then we need to know whether you have where we have paired or unpaired data, whether the data comes from clusters. I think I have an illustration of that. Then if we have non-randomized comparative effectiveness, that's where we actually want to compare, say, two treatments or two different groups on something, but it's non-randomized. Then we have the possibility of selection bias affecting our results, and how do we control for that? And then finally, one thing, I guess, in the end here, if you yourself are not a statistician, you may want to consult a statistician depending on the complexity of your study. So effect size is, just as I mentioned, it's the difference between, say, mean, survival rates, proportions, whatever. So the idea here is like when we're, if we're computing what sample size we need for a study, this is one piece of information that you need to know, is how big of a difference would be meaningful. And then what measure of variability do you have for this outcome? And so you can estimate effect size from pilot studies. You do a small study to get an idea of what differences there might be. You can get effect sizes from studies that are published that are doing similar things to what you want to do. Barring all that, we can do a best case, worst case scenario, given the type of data that you have. Then whether a data is paired or unpaired. Unpaired means that each data point comes from an independent entity. So like patients in treatment groups, you don't have the same patient in both the treatment and the control group. On the other hand, if we have paired data, then that means we have data from the same patient, or maybe it's matched pairs. So this is done in twin studies, obviously, where you have matched, even though they're different individuals, because they're twins, they're matched. If we do paired analyses, then usually that requires fewer patients, has more statistical power than independent groups tests or unpaired tests. But we also then have to deal with within patient variability. And then if we have both types of data, if we have both independent groups and we have paired data, like for example, if patients take some test over, say, a 3-month period, then we've got both independent groups and we have within patient variability that needs to be included in our analysis. So I have just an example here of a study we did some years ago, where we looked at the effect of percutaneous coronary intervention on quality of life in patients with stable coronary disease. And so part of this was to look at these two instruments, the Seattle Angina Questionnaire and the RAN 36, which are quality of life types of survey, and we wanted to look at the effect of whether or not they underwent PCI on their quality of life or their health status. And so this is, in plotting the data over time, you can see that here's the two independent groups, but within each group we have patients measured, the same patient with measurements over time. So we have a different type of analysis that we would need to do here because it involves both independent groups and paired data, in the sense that patients are being followed over time. Then another consideration is whether we have what's called clustered or multi-level data. So what we mean by this is that we have, if we're doing, say we're doing a study, but what we're going to randomize is not individual patients, but we're going to randomize different health clinics or different hospitals. So in one hospital, all the patients are getting the same treatment. In another hospital, they're all controls or treatments or whatever. So the idea is that if some patients are coming from one particular hospital or one particular health institution, then their data may be correlated. And that's what we refer to as hierarchical or clustered data. And so in this type of analysis, we're going to consider two things, what we call fixed effects and random effects. Fixed effects are like our treatment control group. That's a finite set of levels that we want to look at. Random effects then would be, say, the levels of or the different clinical trial sites or different hospitals, maybe different geographic regions. And they would be considered random effects because they would be considered drawn from a potential or from a population of potential health institutions or hospitals that we could possibly draw from. So this, for the Courage trial, this sort of illustrates the hierarchical nature of our data, where we have three different healthcare systems: the US non-VA, Canadian healthcare systems, and then VA healthcare systems in the US. And then within each healthcare system, we have different sites. Obviously more than 2 sites here for each one, but and then within each site, we have patients, individual patients that are randomized to either PCI or optimal medical therapy. And so these are all random effects, because there's obviously we're not getting all US hospitals or all Canadian hospitals. There's these sites are also a random effect, but the treatment group is a fixed effect, because that's what our interest is in, is comparing PCI versus OMT. And then we would have any number of patients at each site, which would also be, patients are always random effects. Okay, and so as I've already mentioned, the data from a given cluster might be correlated. In other words, we can't assume that they're independent, and this may affect our analysis then if we don't take it into account. And then I want to talk a little bit about non-randomized studies and looking at comparative effectiveness analyses. In other words, what we're comparing different, say, treatment groups. The pros of doing non-randomized studies that you actually get more data. The data probably already exists somewhere in a database or in EMRs. It's less expensive to do, and there's a claim that it's more realistic as far as clinical practice is concerned. The cons, of course, is that if you don't have randomization, then you have the potential for selection bias and confounding. So there's some ways that we can reduce selection bias. We can do case control matching, you can do covariate adjustment, we can stratify. And then a couple of things that we will go into next week, a propensity score analysis or inverse probability weighting, and then we can also do what's called instrumental variables. And so those are techniques or methods that are used in non-randomized studies to at least hopefully reduce selection bias. Okay, so with that, I think we're going to, we'll take another, 10-minute break. And then now William is going to get you going on doing Python coding for some of the data that we've looked at. So
I think we got to the part where the overview as far as the statistical aspect goes. So John, you want to come in here?
Yes, I think it's almost 2 p.m. and then we end at 2 p.m. So I think we'll end here and then continue tomorrow. So William, if you would go over some of the Python, I mean, that is also recorded, right?
Yes, that's also recorded, but I do have, so we have an option. I can either go through the material quickly or I can let this go. This might take a little longer. Yeah, this might take a little longer. So it's up to you. We can either keep going and then I come in maybe 5 minutes to time, or I can do a quick 10 minutes as to what the expectations are.
Okay, yeah. I mean, let's discuss that maybe offline and then.
Offline. Okay.
So tomorrow we'll play the Python coding for about an hour, and then we'll continue with the regression and other statistical aspects.
Okay, cool. So
yeah,
then,
because
I
we have up to 3 hours tomorrow, so we can use the 1 hour on this coding and then continue afterwards with
okay, cool. Okay, I think that's a good idea. So we end here, right? Or do we?
Yes, it's almost 2 o'clock. So
okay, so we end here. Okay, cool.
So again, thank you all for coming. I will continue tomorrow. I mean, tomorrow will be the last day for the pre-training sections. Then after that, next week will be all live sections for the remaining week. So we'll see you all here tomorrow, same time, 11 a.m. Eastern Standard Time.
Okay, thanks.
1 second, I'm going to drop the link. I'm going to drop a link to the survey in the chat. If you all could just stay on for 1 second.
Okay, cool. And I've taken the. So let me stop here so that Stacy.
Right.
Yeah. Okay, sure. So let's see, share. Where's the share button? Yeah.